Bismillahirrahmanirrahim. Hello everyone, I hope you are all doing well. I welcome you all to the class of Real Analysis. Our discussion is continuing on chapter number 3, Numerical Sequences and Series, and I am using Principles of Mathematical Analysis by Walter Rudin. Lastly, we discussed concept of convergent sequences. I hope you have seen that lecture. In this lecture, we will discuss a very important concept of this chapter, that is Cauchy sequences and diameter of a set. So let us start from the definition of Cauchy sequence. A sequence Pn in a metric space X is called a Cauchy sequence if for every epsilon greater than 0, there exists an integer n such that the distance, d stand for distance. Walter Rudin is defining this definition in the context of metric space. So he says a sequence Pn is Cauchy sequence if the distance between two terms of the sequence Pn and Pm is always less than epsilon, where n and m are integers and both are greater than or equal to integer n. In other words, after some stages, capital N shows stages. After some stages, this definition hold. The distance between any two terms of this sequence becomes less than epsilon. Alternatively, you can define Cauchy sequence as, in a metric space, a Cauchy sequence is one whose terms eventually becomes arbitrarily close to each other after some stages. After some stages mean, suppose this definition does not hold for first 100 natural numbers. When your n is 101, this definition becomes hold. That is, the distance between two terms Pn and Pm is always less than epsilon for all m and n which are greater than or equal to 100. Another style to define a Cauchy sequence. A sequence is a Cauchy sequence if the distance between the terms Pn and Pm approaches to 0 whenever your m and n approaches to infinity. So these are the three styles to define or to understand the definition of Cauchy sequence. Next, we elaborate this concept by simple examples. The first example is a Cauchy sequence in R, set of real numbers. Consider the sequence Pn is equal to 1 over n and the distance, that is the metric. Metric in R is measured by distance of Pn. Pm is the absolute difference of Pn minus Pm. I am using here the usual metric. In a usual metric, the distance between any two real number is given by x minus y, absolute x minus y. So this becomes Pn. What is my Pn? My sequence is 1 over n, so this is 1 over n minus 1 over m. Clearly, when you take m and n approaches to infinity, then this term is approaches to 0. Similarly, 1 over m also approaches to 0. So the difference is also approaches to 0. So this shows this distance approaches to 0. So according to this result, this sequence is a Cauchy sequence in R, and further it converges to 0. Clearly, when you take n approaches to infinity here, your sequence converges to 0. So this is a Cauchy sequence and it converges to 0 here. Similarly, the sequence Pn is equal to 1 plus 1 over n is also a Cauchy sequence in R, and it converges to 1. When you take n approaches to infinity, here this become 1 over infinity 0, 1 plus 0, this is 1. So this sequence approaches to 1. The next example is from R square, that is the plane. So consider the sequence Pn whose first coordinate is 1 over n and the second coordinate is also 1 over n. Both coordinates are same. For your convenience, I am defining the few terms of this sequence. Sorry for inconvenience. Okay. First few terms of this sequence are when you put n is equal to 1 here, this is 1 1. For n is equal to 2, this is 1 by 2, 1 by 2. For n is equal to 3, this is 1 by 3, 1 by 3 here. Distance in R square is given by square root xm1 minus xn1 plus xm2 minus xn2. xm1 is the first coordinate of pm and xm2 is the second coordinate of pm. In other words, your pm is xm1 the first coordinate and xm2 the second coordinate. Similarly, pn can be defined as xn1 comma xn2. So what is the in case pm, your first coordinate is 1 over m. Similarly, your second coordinate is also 1 over m, because we have defined the sequence as both of the coordinates of the sequence are same. So this become 1 over m minus xn1, the first coordinate of pn. So this is 1 over n. So the first bracket is 1 over m minus 1 over n. The second bracket is also 1 over m minus 1 over n. So this, after adding this, this become 2 times 1 over m minus 1 over n square, and this is equal to square root 2 absolute 1 over m minus 1 over n. By using the result, you know x square absolute is equal to x absolute here. When you take m and n approaches to infinity, this difference approaches to 0. Hence again your metric d approaches to 0. Hence this sequence is a Cauchy sequence in R square. And to find its limit, you have to take n approaches to infinity in both coordinates. This becomes 0 0. So this is a Cauchy sequence and it converges to the origin 0 0 in plane. Similarly, the sequence Pn 1 plus 1 over n 2 plus 1 over n is also a Cauchy sequence in R square and it converges to 1 2. Next we move towards the second segment of this lecture. This is the diameter of a set. This is very easy. Suppose this is my set, some set E, and this set E has some points. Suppose this is my first point, this is my second point, third, 4, 5, 6, 7. So there are finitely many points in this set. Now you want to find the distance between any two points in the given sequence. So clearly these 2 points are close to each other, but if you find the distance of this point from here, this point is far away from this point. So we can find the distance between any 2 points in the set. So the largest distance between any 2 points represent the diameter of the set E. This is same as in case of circle. This is the particular example. There are infinite many points in the circle. but the largest distance between the 2 points is given by its diameter, that are the opposite point on the boundary of the circle. So we properly we can define this definition as, let E be a non-empty subset of a metric space X, then diameter E is denoted by dim of E, and it is defined as, diameter of E is the supremum of the distance between 2 points of set E. So the diameter measures how far apart the points of the set can be. There are some important remarks about diameter. If your set E is bounded, then its diameter is always finite. If your set E is unbounded, then your diameter is infinite. For example, simple, we take a finite set 1, 2, 3, 10. The diameter is clearly the difference of lower and the upper element of this set, that is 10 minus 1. This is equal to 9. So this represents the diameter of E. But if you take your set E is a set of natural number, that is the positive integer 1, 2, 3 up to so on infinity, there is no end point of this set. So in this case your diameter will be infinite here. The third remark is, if the set E is singleton, that is there is only one point, then diameter is clearly 0, because suppose this is my singleton set. Now when you find the difference of this set from this point from itself, this will become 1 minus 1, this is 0. So in this case your diameter is 0 here. There are some examples. Consider the interval 0, 3. The distance between points satisfy x minus y. I am taking here the usual metric. X minus y is less than or equal to 3. The largest distance occur between 0 and 3. So thus the diameter is equal to 3 here. Next example I am taking from R square. Let E is the cross product of two closed interval 0, 1, 0, 1. Geometrically, if you observe, this is the unit square. You can draw it here. This is x is equal to 0 and x is equal to 1 here, and this is x is equal to 0, y is equal to 0, this is y is equal to 1 here. Now if you join all of the points, this will become a square. So this is your E. Clearly this point is has a coordinate 1, 1, and this point has a coordinate 0, 0. Now the largest distance occur between these two corner points 0, 0 and 1, 1. This is the largest distance. The largest distance occur between the corner points origin and 1, 1, and this distance is given by using simpler distance formula 1 minus 0 square 1 minus 0 square, that is equal to 2. So the diameter is equal to square root 2 here in this case. Next, this is a very important fact. This is very important. Relation between Cauchy sequence and the diameter of a set and the geometrical interpretation of Cauchy sequence. What is the relation between Cauchy sequence and a diameter of set? Let Pn be a Cauchy sequence in a metric space X. Consider the tail of the sequence. Suppose this is a set En which consists on all those points of a sequence, all those terms of the sequence for which your index n is greater than or equal to n. For example, this set En consist on these term of this sequence. The first term is n, second is n plus 1, third is n plus 2, up to so on. So this is the set En that consists on tail of the sequence. Tail of the sequence mean, suppose this is my sequence Pn, that is a Cauchy sequence. Suppose I take clearly the first term of this sequence is denoted by P1, the second term is P2, up to so on. There is a some integer n, capital N. So this is the nth term of this sequence. Now the next term will be Pn plus 1, other will be Pn plus 2, and up to so on. So we are taking only these terms which are greater than or equal to Pn. So these terms, we are calling this term as the tail of sequence. I hope now you are clear about this concept. So this is the set of all terms after index n. Now we compute the diameter of this set. Now I want to compute diameter of En. What is the definition of diameter? Diameter is just the distance between the two terms, any arbitrary two terms of this sequence. So of this set, as En consists on these terms for which your n is greater than or equal to capital N. So we can take the distance between only those terms whose index is greater than or equal to n. So suppose I am taking the mth term and the nth term, and we apply the condition these two terms are greater than or equal to n. So we are interested to find the distance between Pm and Pn. So after finding the distance between every two terms for which Mn is greater than or equal to n, and we take the supremum. So this shows the diameter of En. On the other hand, as Pn is a Cauchy sequence, we can define Cauchy sequence as Cauchy. If Pn is a Cauchy sequence, then this distance is always less than epsilon for all Mn greater than or equal to n. Now combine these two. This set consists on all those terms whose distance is this set. In this set, we are interested to find the distance between all those terms which are greater than or equal to 10 is equal to n. On the other hand, Cauchy sequence says this distance is always less than epsilon. That means all distance in this set En are less than epsilon. Thus, the diameter of En is less than epsilon. So the Cauchy condition mean the diameter of the tail of the sequence becomes arbitrarily small and the diameter approaches to 0. Hence, a sequence Pn, this is the last line that will clear this concept. Hence, a sequence Pn is a Cauchy sequence if and only if the diameter of its tail tends to 0. That is, diameter of Pn is approaches to 0 where n is greater than or equal to n. For example, I have a sequence Pn is equal to 1 over n, and I want to check whether this sequence is a Cauchy sequence or not. The simple concept is that you have to find the diameter of the terms of this sequence after some stages n. If the diameter of the terms of this sequence approaches to 0, then absolutely this sequence will be a Cauchy sequence. So I hope everything is clear now. If anything is unclear, you can ask me. Inshallah, I will reply you. So see you in the next lecture. Take care. Allah Hafiz.